Hello friends, welcome to my channel. Let's have a look at the newly appeared problem, that is problem 2378, choose edges to maximize score in a tree. So in this video, we are going to share a DP solution, that is dynamic programming. So first, let's look at the statement of the problem. So we are given a weighted tree consisting of n nodes numbered from 0 to n-1. The tree is rooted at node 0 and represented with a 2D array called edges of size n, where edges I equals parents I and weight I, indicating that node parent I is the parent of node I, and the edge between them has a weight equal to the weight I. Since the root does not have a parent, so we have edges 0 equals -1 and -1. So we want to choose some edges from the tree such that no two chosen edges are adjacent, and the sum of the weights of the chosen edges is maximized. So that's the key for this problem, the key requirements. So we are required to return the maximum sum of the chosen edges. So here are two notes. First is that we are allowed to not choose any edges in the tree. The sum of weights in this case will be 0. So in other words, the result will be always non-negative. Secondly, two edges, edge 1 and edge 2 in the tree are adjacent if they have a common node. So this item basically is a formal definition. So here is example 1 and example 2. So we're going to walk some details using example 1. So here example 2 tells us that the tree here we are considering is not necessarily a binary tree, right? So the constraints on this problem are listed here. First, the number node can be up to 10 to the power 5, so which is a large number. And the edges length is 2, right? So it's some information about the parent node. And also, there's no self-cycles, and the weight can be negative, right? It's bounded in absolute value by 10 to the power 6. And the edges represents a valid tree. So a tree is actually a special type of graph. So the node number is n, and the edges number is n-1, and it's singly connected. So that's actually a definition of tree from the graph point of view. So with that said, let's look at the analysis. First, our method is going to be dynamic programming. So we're going to use some cache or memorization. So first, for each node u, so we're going to compute two values, s1 and s2. The meaning or the interpretation of s1 and s2 for this node, specific node u, is the following. So s1u means the maximum sum at u if we use one u and the children edge. So if we can, right? If we have the children. So note that we can only use one, right? So based on the problem requirement. So s2u is interpreted as the maximum sum at u if we do not use any u2 child edge, right? So that's the interpretation. So it's going to be important, and keep this in mind. So next we are going to do some analysis. So I would suggest that I can draw some pictures in order to digest the analysis. So because we want to find a recursion relation, right? So first, let's notice the base case. The base case is corresponding to the case for leaf nodes. So for each leaf node, s1 and s2 are 0. So this is actually straightforward or trivial in some sense. So next, we are going to explain the update rule. So first, let's introduce some terminology. So here, again, the tree is not necessarily to be binary, right? Assume that a node u has subtree represented by v1, v2, vi up to vm, right? The computation of s2u is actually very easy, because s2u means that if we do not use any u to vi edge, right? So in this case, we can freely use or not any vi to its child edges. and each vi. And therefore, so S2u is the summation of the max S1 vi and S2 vi for all the i's. In other words, we find the this number, maximal of this number for all the subtrees. So you can interpret this formula using the interpretation of the definitions of S1 and S2. So this is actually a very simple case. So next, we are going to compute S1u, right? So in this case, we can consider one generic edge, u to vi. Assume that we use this edge. Let's see what sum we can get. So let's call this sum temporary I, just for fixing the idea. So in this case, because we want to use this edge, u to vi, we want to add this one, right, du vi. And in this problem, if the edge is negative, we just replace the one by 0, right? Then for the sum we want to add at node vi, so we could only consider S2 because we cannot use any vi to its subtree edge, right? So that's the second part. So then actually we consider other subtrees. We need to summation all those numbers, right? So this is the sum we can get at subtree vg, right? So we summation all the sums at those subtrees that is not subtree vi, right? So that's the sum if we use one edge from u to vi, right? So the S1u will be the maximum of this temporal I variable for I runs from all the subtrees. So here is a specified explanation. So we use S2 vi because we have used u to vi. Hence, we cannot use vi to its child edge anymore. So the part summation of max S1 vg, S2 vg for those g does not equal I is nothing but S2u minus max S1 vi and S2 vi, right? Because this sum is sums for all the subtrees. So this sum is summing all the subtrees except subtree vi, right? So it equals S2 minus the sum at vi. So S1u will be the maximum of those temporary variable I, right? For I running from all the subtrees. So that's the update rule for S1u, right? But now we computed S1u and S2u. Then actually it forms a full solution. So let's do a walkthrough for example 1 so that we can get a better understanding, right? So first we notice that 1, 3, and 4 are leaf nodes. So for these 3 nodes, we have S1 and S2 equals 0. That's actually the base case, right? So now let's look at node 2, right? So S2 node 2 is very simple to compute. So we compute the maximum of S1 at node 3, right? And S2 at node 3, then plus the corresponding one at node 4, because we do not use any of the edge from 2 to 3 and 2 to 4. So we can use the sum at 3 and 4 freely. So this gives us 0, right? To compute S1 at node 2, right? So we can consider using this this edge or this edge. So if we use the edge from 2 to 3, right? So the sum is the following. So we need to compute this edge and then plus S2 at node 3, right? Then plus the maximal we can get at node 4, right? Because we do not use this one. So in this case, we get 6 plus 0 plus 0, that is 6. Then we can also consider to use the edge from 2 to 4, right? So in this case, the sum is 4 plus S2 at node 4, then plus all the things we can get at node 3, that is this expression. So this gives us 4 plus 0 plus 0, that is 4. So S1 at node 2 will be the maximal of 6 and 4, that is 6. So therefore, for node 2, we have S1 node 2 is 6 and S2 node 2 is 0. So next, we're going to compute the information at the root node, that is at node 0. So for S2 at node 0, because we do not use this edge or this edge, so we just sum the information at node 1, that is max of this expression, and max at this node 2, right? So this gives us 0, and this gives us 6. So 0 plus 6 is 6. Then we're going to compute S1 at node 0. So for this case, we can consider to use 0 to 1 edge. So in this case, first let's do the sum. Take this edge, that is 5. And then we're going to add S2 at node 1, right? Then we can add whatever we can get most at node 2, that is max of S1 or S2 at node 2. So this gives us 5 plus 0 plus 6, that is 11. And then we can also consider to use the edge from 0 to 2. So in this case, if we compute sum, let's first add this edge, that is 10. Then we're going to add S2 node 2, because we cannot use 6 or 4 anymore, because we have used 10. So that's why we have this term. And then we can collect whatever we have at node 1, that is max of S1 or S2 at node 1. So in this case, we can get 10 plus 0 plus 0, that is 10. So for node 1, node 0, so the S1 is max of 11 and 10, that is 11. So therefore, for node 0, we have 11 and 6. So the return actually will be the maximal of S1 and S2 at the root node, that is 11 here. So max of 11 and 6 is for sure 11. So this actually finished the walkthrough. So the code actually is very straightforward as we understand the logic. Basically, we just translate these two update rules in our code. So we're going to do a line-by-line analysis for the code we're going to write. So before we do that, here is a suggestion. So actually, we can draw a graph and digest the analysis above. So with that said, we are ready to write the code. First, let's do some preparation. So I prefer to first build a graph. So in this case, in this problem, the graph actually is a tree. So all I can see is a directed graph. So I'm going to use a container. Let's see, collections, default directory. So I'm going to use a dict to hold the neighbor and the weight of the edge, or the length of the edge. So this is actually very simple. So just a for loop, right? For node and parent and the edge length in enumerate edges. So here is a set case to consider. That is, originally we have the root. Root has no parents, so we're going to check if node is greater than 0, right? In other words, it's not the root node. Then we're going to graph. So the parents, right, it has a child, that is node, and the edge length is W. So that's it. So we have finished build the graph. And the second step is to do the DP, dynamic programming. So basically, we just do a verbose translation of the above analysis. So in this problem, due to the size of number of nodes, I'm going to use memorization or using cache. So for this, I'm going to define a function. Let's call this f. So the role of f is actually compute S1 and S2 for each node. And let me make some annotation so that you can better understand. So we're going to return a tuple that is S1 and S2, right? So S1 is the maximal sum if we can use node child edge. Notice that we can only use one edge if they have a number of children. So S2 is that the maximal sum if we do not use any node to child edges. So So that's the return and their interpretation, actually as explained in above. So first, let's look at the special case, if not graph node. In other words, so this node has no children. It's a leaf, so we're going to return 0, 0. So you can use this parentheses or just write like this, 0, 0 is okay. This is corresponding to a leaf node. Let me remark here. Now let's consider the generic case. So in order to consider generic case, I'm going to first initialize S1 and S2 to make them 0, and then we do the update. So we need to check the neighbors of the current node, right? The neighbors actually is not necessarily just 1 or 2. It can be many in principle. So let's first track this information. Let's call neighbors equals graph node. Notice that this is a dictionary, right? It contains the neighbor information for this node and the corresponding edge length, right? So that's the neighbors. So now let's first determine S2 at node. So this is actually very simple. So because for S2 we do not use any edge, right? So we can use the maximum sum at the neighbor nodes, right? So basically we can write for neighbor, for children in neighbors. So we can use children to its children edge, or we can choose not. So in other words, we just need to summation all the things. So that S2, so increment by max of the S1 and S2 at this node, at this children, right? So that's actually sets the S2. So here let me make some annotation so that we can better understand that. So because we do not use any node to child edges, so we can freely choose to use or not the child to its child or edge, right? In other words, so we can choose at each children the maximum of S1 and S2, then add to the S2 for this node at hand. So this is the first case. So this is actually the easy case. So next we're going to determine S1 node, right? For this actually depends on depending on our analysis here. So we're going to compute this sum and compute its maximum, and especially notice this relation, right? So this summation is nothing but S2u minus the max at the subtree we are considering. So with that said, let's do this. So first let's write the code. So for child in neighbors, first let's introduce this temporary variable corresponding to the temporary I above. So first I'm going to compute S2 minus max f at this current children corresponding to the vi above. So this is actually the third term here, right? And then we are going to compute the add the edges, right? So now let's add the edges. So edges length is nothing but neighbors, the child. So but you know this number can be negative, so then we can use this max of this children, and with 0 this will make sure we're adding non-negative things. And then we're going to add f children at 1, right? In other words, this is corresponding to the S2 and the children, because when the tuple is 0 indexed, 0 means S1 and the 1 means S2. So this corresponding to this term, right? S1 vi. So this is the edge, and this is the first term, that is S1 minus this marks of S1 and S2 as the children. So that's it. So each time we compute a sum, so we're going to update S1 by max of the previous state of S1 and the current temp. So that's the code for this one. Then we're going to return S1 and S2, right? So here, so if we do not consider the annotations, this code actually is very short. So, but for understanding, let me add some annotations here also. So we can only use one of the node child edges, right? So for the children, we use the node child edge. So we shall consider the sum corresponding to not use children grandchildren edge. So that's the interpretation of this code, right? So that's about it. So as we mentioned, the size of the nodes is large, so I'm going to use cache or memorization. So with that said, we have prepared the dynamic programming hyperfunction. So what we are going to do is actually return the f at node 0, right? So what we want to return is the maximal of this 2 returned. So that's the full code for this problem. The code actually is very short. So as we understand the logic, so things actually are clear. So first, let's do a special case check. Yeah, it passes the first example. So the first example is a binary tree, right? So now let's do a generic case check. Yeah, it passes all the generic case. So now let's give a quick summary of this solution. So first, we build a graph so that we can easily track the parents and children relations, right? Then we write a dynamic programming hyperfunction. So this function actually is like a recursive format of traversal. So then we are going to prepare the return. We return the maximal of S1 and S2 at the root node. So basically that's about it for this specific problem and this video. So as we suggested, it's good to draw a graph and digest the analysis above. So with that said, I guess that's it. Thank you very much.